So what I want to talk is about a novel approach to supersymmetry in which you are not forced to work with the standard supermultiplets. So this talk is based on these works in which we presented the idea in 3 dimensions first, and then we apply it in 4 dimensions. And also as an extra result, we found some interesting geometries. So flat geometries in which the rotational invariant black hole in 3 dimensions can be embedded. These are the collaborators, Jorge Zanelli, Mauricio Valenzuela, the students Pablo Páez and Salgado, and Eduardo Rebolledo. He's now in Colombia. So the motivation is more or less clear for many of us. It's like supersymmetry, we all know, is under serious threat by the result of LHC. Even if it's found supersymmetry, a serious problem will arise with respect to the level of naturalness and fine-tuning that is required to make sense of the theory. And so that's just a very general reason of why it's interesting to study models that offer an alternative to MSSM models. But also we have these other tremendous problems like the cosmological constant problem and so on and so forth, quantum gravity, etc., etc. So the main idea is to, by a simple trick, be able to include matter in a gauge connection and then circumvent the necessity of doubling the number of states to implement supersymmetry. So I'm going to explain the idea using the model in 3 dimensions, and I'm going to describe how to define a gauge connection, how to write down an action principle, and how the symmetry works in this scheme. And I will show that the actual theory that results from this framework makes sense, and there are classical solutions, and it's free of ghosts and things like that. Then I will show what happens in 4 dimensions. Things are more complicated. And then I will close with some final remarks. So in 3 dimensions, many of what I'm going to say here is true in general, but I'm just using 3 dimensions because it's simpler and it's a smaller representation. So the idea is to include fermionic fields, psi, such being 1/2 field, in a gauge connection directly. So by doing that, treating matter and gauge bosons in a more democratic way, so more faithful to what the basic idea of supersymmetry is. So obviously, fermionic matter is not a one form. So a way to include it in a gauge connection is to use the local frames, the Filbine, which are one forms, and then contract them with the gamma matrices. In particular, in 3 dimensions, we can use OSP21 or OSP12, and then we will have 8 traceless generators. So an internal U1. The spinor. This spinor for us will be a charge spinor, and we'll have the Lorentz spin connection. And we are not going. We are free to. In this representation, we don't have translations. It's just a super extension of Lorentz. So we are not going to include the Filbine there. Okay, this is the superalgebra. It's a We in particular use a representation of 3 by 3, so we have 8 generators, traceless generators.
Is there an obstacle to including translations, or you just not presenting?
For the actual, a priori, it isn't an obstacle. But in this approach, it gives you more flexibility. So I'm going to obviously talk about that in the next slides when the symmetry transformations are defined.
Another important point is to say that not any superconnection is in this form. You're making some assumption on the form of the superconnection because you have that by the Suzy power.
Yeah. So normally, if you want to write down the supergravity action in 3 dimensions, or in any dimension, you will have a Rayleigh-Schwinger field here. Sometimes it doesn't work. And that would be a one-form fermionic. But the trick that we are doing here is using a composite field. So we are. I just want to remark that, but I'm going to go back to that when I discuss the supersymmetry transformations, because it's the tricky part of this approach. So just to left a note, it's not usual. It's not a usual connection in the sense that here we are introducing composite fields. And so we are going to treat at the end the field line and the spinor as dynamical fields. We are going to treat all the fields that are in the gauge connections as dynamical. Even though it could be possible also to treat the background as a fixed background, and that possibility has been explored by Alfredo Iorio and others to describe fermions in graphene and in curved layers of graphene. But I'm not going to do that. I'm going to consider every field as dynamical. So the obvious action is the Chern-Simons action in 3 dimensions, which is was invariant under OSP 22. These are the usual gauge transformations. And expanding the action, we get the Chern-Simons, the abelian Chern-Simons for the electromagnetic field, the Chern-Simons action for gravity. So sometimes this is called exotic gravity. It's not Einstein-Hilbert in 3 dimensions, but it's Chern-Simons term. And then the minimal coupling, but acting over the composite field. So this nabla is the covariant derivative in this for U1 times Lorentz in the spin 1/2 representation. So expanding the fermionic Lagrangian, we get the minimal coupling for this Dirac spinor, plus a non-minimal coupling by means of the torsion tensor. As we will see, this behaves as an effective mass term in a semi-classical approach for this spinor. So TA is the torsion tensor, is the covariant derivative of the field line. It can be expressed by means of the contortion, assuming that we can decompose the spin connection in the Riemannian part plus the contortion. And so this action is clearly diffeomorphic invariant, and there is local invariance under U1 and Lorentz. And there's an extra built-in symmetry which came from the fact that we use this funny way of implementing the fields in the connection, which is this Weil scaling. If we scale the field line and the spinor in opposite ways, then the action is invariant. Okay, so the symmetry transformations. This is an element of the group. It's a zero form. Here we have the parameters, the U1 parameter, the Lorentz transformation, local Lorentz, and then local supersymmetry. Using the usual rule for gauge theory, so the transformation is given by the covariant derivative, then we can deduce the transformations for all the fields. And under these general transformations, the Lagrangian change up to a boundary term. But now the tricky part came in how to define the transformations in our fundamental fields, the spinor and the fieldline. Because we are on the left-hand side, we have the variation of both of them. So we have to decide to give an extra input. So where are we going to put the transformation when we on which field we are going to put what part of the transformation. So for U1 and Lorentz, the answer is very obvious, because under U1 we know that the U1 doesn't act trivially in the Lorentz indices, and also on the other hand, for Lorentz transformation is the same. The local frame has a vector index in the tangent space, so you make it transform in the usual way, and by doing so, also the spinor receives the correct transformation with all the signs correct, no opposite sign. All the usual Lorentz way. So the tricky part came with supersymmetry transformations.
Can I just ask why sort of, at least classically, why am I worrying about these fundamental fields? Why are we calling these fundamental? Should I just do a field definition?
Because I'm not really surely I could do supergravity. Surely I could do that, but I'm interested in how to implement matter in the gauge connection. So that what I would have by doing that, I would read a Tringer field. So, but I want to implement matter.
I guess I'm trying to understand how you're going to get something different. I mean, classically, it seems that you can't. It's just a field definition.
Yeah, no, but there are. So, as I will show in the next slide, It's not as simple as that, because supersymmetry can potentially turn on the spin 3/2 degrees of freedom. So you have to keep that under control. So the couplings in the theory, they could also dynamically do that. So that's the risk. And so the complicated part comes here in supersymmetry. The solution that we found the easiest solution was to demand that the field line was invariant under supersymmetry. And I'm going to explain why and how. So this is what we have on the left-hand side. So we have the variation of the field line and the spinor, and then that's proportional to the covariant derivative of the spinorial parameter. And so the only option, or at least a very obvious option, is to demand to stay in a linear representation, is to demand the invariance of the field line. So basically you are demanding by hand no gravitino. And then you can express the supersymmetry transformation of the spinor in this way. So by definition, we won't have gravitino doing that. So what happened to the irreducible parts of this field? So here I denote phi is a Rayleigh-Tringer field which contains the gamma traceless part, which is the Rayleigh-Tringer, this chi, plus the spin 1/2 degrees of freedom, the psi. And so we have, if we want to impose these conditions, then we have to check that the spin content both sides of the equation is balanced. So by multiplying by this spin 1/2 and spin 3/2 projectors on the left and on the right, we get using the spin 1/2, we get this expression. So the definition of the transformation for the spinor, and using a spin 3/2, we get a consistency condition for this manipulation to be valid. So I just want to remark also that this contraction, gamma mu psi alpha, is by construction gamma traceless. The gamma traceless component of that contraction is trivial. So what we are doing is, what I'm saying is that in the original connection there is no right trigger, but we also have to check that the interactions in our theory are not going to turn on those degrees of freedom. And so applying the 3/2 projector, this is the condition that we arrived to. So the projector acting on the covariant derivative of the spinorial parameter has to be 0. So a solution to that is to demand that the covariant derivative of the parameter lives in the kernel of this projector. And by doing that, we also check that the spinor is pure gauge. Yeah. So I have to remind you that gravity in 3 dimensions is a topological theory in the sense that the degrees of freedom are global. Okay, so this is not so strange. So this consistency condition implies now if you want to solve these equations, then you have to specify the background. So the invariance and the supersymmetry of the solutions of our theory will depend on the background, as usual in supergravity. So the number of supersymmetries that remain for the background or the ground state of the theory will depend on the actual nature of that background. So, for instance, just to show that there are solutions, non-trivial solutions, here for flat space, you will acting with further covariant derivatives. Here you can deduce an integrability condition of this on this parameter, and then you can see that the supersymmetry has to be global. So this looks very much like a conformal supersymmetry. But so these parameters have to be these spinorial parameters are constants, even though there is a next coordinate dependence here. That is not a local transformation. And also solutions exist for flat space and a non-trivial U1 connection. Yeah. Okay, so just a remark. There are other. This is some sort of nonlinear representation of supersymmetry. There are also they have been studied also other nonlinear realizations of supersymmetry. There are 2 famous ones: the Volkov-Akulov theory and the inverse Higgs mechanism. But I'm not going to discuss that. And also similar ideas come from Kirill that consists in these pure connection gravity theories, and this spinorial include matter in spinorial 1 forms. Okay, so now we wanted to see a little bit of the physics that is appearing from this theory. So what we have is basically the condensate of the fermion is acting as a dark energy source. So solutions are conformally ADS. We have conservation of the current. We have the Dirac equation for the fermion. And another funny aspect is that the field equation for the field line will be also the conservation of the energy momentum tensor, and actually more stronger than that, it will be a vanishing on-shell energy momentum tensor. But you can rephrase that by saying that the torsion is going to be sourced by the energy momentum tensor of the matter field of this spinor. That can look a little bit strange, but this is just the fact that we start on the gravity side. We have this exotic gravity, which is the Chern-Simons form for the spin connection. That kind of, so it's not so weird. So in the equation for the spinor, we have this kappa term, which is the totally antisymmetric part of the torsion tensor. So the thing is, the most general solution to this. By Bianchi identities, we know that the covariant derivative of the torsion tensor is proportional to the contraction of the Lorentz curvature R, AB, EB. So we know that in this system that it's going to be covariantly constant, this torsion. So the most general solution to that is this expression. So that is telling us that the only component of the torsion here is the totally antisymmetric part. If you replace that in the equation for the spinor, that looks like a constant. So that's why we call it an effective mass term.
So I have a question. You impose that the frame field is related to the connection, or it arises as a consequence of the field equations?
That
so
with
status of that equation. Usually, frame field should be related to the spin connection. Do you have it happening here or not?
No, we don't impose anything extra besides the field equations. So what you can do here is to try to algebraically solve for the torsion. So, I mean, here you will have the Riemannian component of the spin connection plus the contortion and the field line. Those are your independent fields.
And if you solve for the torsion, then you know the spin connection.
Yeah, what you solve is the contortion. And the Riemannian, the Riemannian one is the one that is defined by the field line. So now I'm going to show some classical solutions for the background. But at this level, the spinor can be on. It's on. So we have the Dirac equation with a mass term, without still solving for the background. So a very nice question is if we can actually find solutions with non-trivial, with matter here, solving analytically for the spinor. And a possibility is that maybe perturbatively we can do that, find exact solutions. Okay, so now I'm doing maybe what you were asking. So you can split up the spin connection, the Riemannian part, the omega bar, and the contortion. So the contortion is already specified. We can find the most general solution for that. even with the spinor on. Now, if we turn off the spinor, then we can actually find more solutions easily. And so the field equations tell us that there has to be a Lorentz flat solution, and replacing the contortion here, we get that the Riemannian curvature has to be a solution of negative Riemannian curvature. So now we can use the frames of ADS or the rotating black hole in 3 dimensions, and that will solve the equations. So we can use the BTZ black hole solutions, and we have all of these cases: the extremal, ADS, and the massless black hole. And something very nice is that we can find killing spinors that remain for these solutions. So now I'm probably going to say it wrongly, but so we have for the ADS, I think that we have the full set of killing spinors. For the massless black hole, we have half of them. Maybe for the extremal, 1/4 of the supersymmetries. So those killing spinors are granting that our ground state is a BPS state. It's invariant under supersymmetry. So many times that is enough to say that the solution is stable. So now what happened in 4 dimensions? Well, things are obviously more complicated because you don't have Chern-Simons actions. So
before you go to 4 dimensions, you mentioned that such actions were used in some physical context in the field.
Oh yeah.
It was this Chern-Simons action?
So he was exploiting a system with Weyl invariance. Not Chern-Simons, but just.
What was this idea of putting fermions in the connection?
The main idea is to use graphene to study, for instance, Hawking-Unruh radiation. To put a curved slice of graphene and then maybe be able in the laboratory. Not necessarily, but for them, the Weyl invariance was a key point. And here we have, but the action is invariant and has the Weyl invariance. The solutions break it. When you solve for the torsion, you are breaking this Weyl invariance, and that is what giving mass to the spinor. But yeah, Alfredo Iorio was exploiting the idea, but there are difficulties, but it's still a very appealing idea to maybe test some semi-classical gravity effects in a layer of graphene with a effective speed of light and everything, but still. Okay, so in 4 dimensions, we have to go to a bigger representations. There are no Lorentz super extensions. We could use actually chiral. So a super extension of SL to C or to R, I'm not so sure. But we actually choose to work with USP 221 because we can include we can use a charge spinor here. So we have a U1 internal gauge field, the same trick for the matter, the dual field to translations in ADS or DS, and then the Lorentz generators. So the question is what kind of invariants we can use as valid action principles. So the obvious choice are Yang-Mills type of actions or McDowell-Mansouri formulation of supergravity. Because otherwise, invariants are typically of topological nature, so they won't have a proper kinematic term. So following the same ideas of McDowell-Mansouri supergravity, we have to consider invariants under a smaller group. And so, what are the possibilities? So the original McDowell-Mansouri formulation of supergravity is to take the Hodge dual. You start with ADS, and then you have indices in ADS, but you take a Hodge dual in the Lorentz indices. So you are going to break down. You are going to remain only with Lorentz local invariance. In the case of pure gravity, you can recover the ADS translations by using also diffeomorphisms and the torsion-free condition. But in general, with the spinning matter will source the torsion, so the theories won't be torsion-free. Even the fact that I had here the non-minimal coupling to the torsion, that is not what is caused. That is not what it caused that the torsion is being sourced by the fermion. That's a generic feature of the spinors in a curved background. So in that respect, this is nothing special to what would be a minimally coupled spinor in a curved background. And so, okay, possible invariants are we can obviously choose to apply the Hodge dual operator into the U1 curvature, and then try to mimic the same in the gravity in the ADS curvature. So that way we will know that we will have the correct kinetic terms for Yang-Mills and gravity. But then we have the choice to what we do with the spinor and with this field which is dual to translations. If we naively apply the Hodge dual to the spinorial components of the curvature, then we will end up with second order derivatives in the action which we don't want. And so at the end, any change that you do will cause a problem in one place or the other, and at the end the only good possibility is this P6, which is to use this combination, so the Hodge dual in the U1 and a dual operator in what is left, which is gamma 5, which is a normal operator that in the spinorial representation of ADS will give you the epsilon tensor for the trace of a true Lorentz generator. So since you want to have Hansen-Hilbert, which is like epsilon r Filbine, so you want to obtain this epsilon from some bilinear trace, and that came from the trace of GAB, GCD, and gamma 5. That's epsilon A, B, C, D. And gamma 5 break the ADS translations. Okay. So the resulting action is Yang-Mills, in this case electromagnetism. We have Hansen-Hilbert with cosmological constant and a topological term, and the minimal coupling but over the composite field. So in order to do that, you have to do this 1000 identification to identify the FA field with the local frame, which you can do because the equations of motion that came from this action tell you that the FA field, the little f, is non-dynamical. So you can algebraically solve for it, and a valid solution is this this identification with the local frame, which seemed fair enough for us. A funny fact is that the correct sign for the gravity action came for ds, so de Sitter. So and another interesting fact is that the spinor, there appear four fermion contact interaction for the spinor, which I will talk in the next slides. All right, so we have Young-Mills, gravity, the Dirac fermion, a mass term coming from this is a mass term coming from the fact that we identify the FA field with the local frame, a non-minimal coupling by means of the torsion tensor, and the Nambullino-Lasinio term, this 4 fermion contact, 4 fermion contact term. T mu is yeah, sorry, it's just the torsion tensor. It's just the curved space component of the torsion tensor. And so now, also, the fact that we are using, so in 3 dimensions, we didn't care about that because the physical units came in the right way. But since you're doing this contraction in the gauge connection, you have to have a dimensionless field there. So your psi field doesn't come up with the right physical units. So it doesn't come with the dimension of mass 3/2. So you have to multiply it by a quantity with the correct dimensions, which doesn't have to be necessarily equal to this mu constant. And so now we have several scales in the theory. So the usual theory is just F dual F. So all the scales are hidden in the Lie algebra, but now at the end we have to restore them and to see what are the physical consequences. So we have a term which is plays the role of fermion bare mass, the Nambullino-Lasinio coupling constant, so which is goes here. The Newton constant, which is proportional to, so this little mu will play the role as the Planck mass. We have a term, the Baire cosmological constant came as a mu square, and then since this is a non-normalizable theory, this is an effective field theory, so you have to introduce a cutoff here. The Nambullino-Lasinio term was used for dynamical symmetry breaking and the generation of mass without a scalar. So you are breaking chiral invariance. And the contribution to the effective cosmological constant also include the web of this spinor. And this mass Nambullino-Lasinio is what I'm going to show here. So this is a paper, the old classic paper by Susskind, which addressing the question why of the the fine-tuning that is required when we use a scalar for spontaneous symmetry breaking. So we know that the scalars receive radiative corrections. So one possibility was, before Technicolor, proposed by them, was to use composite fields and of QCD states. So now that is experimentally more or less ruled out. But so for that reason, I mean, this is not a QCD composite state. That is not a possibility. It has to be something else, if anything. So this is the equation for the mass. This is the bare mass, but now we have to include the effects of the curvature and the electromagnetic field for this to compute the Nambu-Lacinier mass. So this bare mass is has to include that. So this is just a very rough approximation of what would be the real computation, and it's just to show that there are chances that it's possible to reduce the amount of fine-tuning needed. The thing is, this is the bare mass, and here we have the other constants. So since the cutoff is, well, this function fu that came from the Balatin diagonalization of whatever method you prefer to use to compute the mass of the Nambu-Lacinier, given by the Nambu-Lacinier term, is a function that has a very good behavior. So this is normalized to the cutoff scale. So 1 would be a mass of the cutoff scale. But the fact that so this is number of colors and number of flavors. I was doing the abelian case, but this in principle you can use a bigger supersymmetric algebra, including a non-trivial internal symmetry group. So, but this is at the end order 1 coefficient, and then we have Newton constant times the cutoff. So this number would normally be wherever you want to put your cutoff, being usually several orders lower than the Planck scale. So we will have a very small number here, and you end up that so you can see that in principle no fine-tuning is needed. The bare mass is proportional to the actual mass of this to the physical mass of this spinor. So it might be possible to improve problems of fine-tuning. Okay, another applications for these sort of theories have been, first of all, coming from Einstein-Cartan theories, and so theories that they have the property that at lower densities they coincide, they reproduce all the classical results of general relativity, but at high densities they could violate energy conditions by means of the coupling of the torsion with this with the spinorial any spinorial source that you are considering. So in principle they offer frameworks or models for cosmology, early universe cosmology with bouncing cosmologies, and also ways to avoid the singularity theorems.
Sorry, can you just come back to the last slide? I lost track of it. So is this the mass of a scale at the correction, or is this fermion mass? What's this the mass of?
So the physical mass would be this U, which is normalized by the cutoff.
Which is that's a fermionic mass, right?
Yeah.
Okay. So this is So if I include a scalar like Higgs, just the thing that I'm worried about, right? What's you saying you get similar behavior?
Yeah, no.
Okay, so
I'm not thinking in adding a scalar here.
Because fermionic masses are protected by chiral symmetry, so you're not really worried about those. So it's the scalar guy that you care about. So this M naught, that's the mass of what?
That's the so that would be the masses that contribute to the bare mass. So in
fermionic mass, right?
Yeah,
so
fermionic.
I don't know what you're talking about. So I'm a bit puzzled by, I mean, even in standard model, I don't worry about fermionic masses are protected by chiral symmetry. And they know where the mass goes to zero, so they're natural.
Yeah.
The problem is scale is the Higgs.
Yeah.
Right, which is a scalar. So
Yeah, but
I
yeah.
know how supersymmetry fixes that precisely because you can relate a Higgs mass,
Yeah, the thing. Yeah.
which is fermionic, which is protected by chiral symmetry. So you haven't got the superpartner here, so it's not at all obvious.
So the thing is, you want to break the symmetry, give masses, can generate a gap of masses. And
I don't know why you're worrying about the correction to fermion.
the thing is, here we have you could say, okay, it's the same, but now I mean, this is your field. It's a composite field. That's a scalar. This is the condensate of the fermion.
So it's an effective mass of a scalar.
No. I just show that as a.
Okay.
We have 5 minutes.
Yeah.
To wrap up.
So it was prior to. It was one of the reasons to propose Technicolor, but here the difference is that we don't have a composite of QCD states, so we're not worried about the facts that they rule out. The same facts that rule out those models, because this is not a Technicolor composite. Okay, so other applications to this came from cosmology and singularity theorems, but difficulties are present, and there are problems in this. In any bouncing cosmologies, there are problems with anisotropies. They could be generated, so you have to check that somehow your theories don't generate them. Also, problem arises when you use an spinorial inflaton, that you won't generate the correct spectral index and things like that. And but the thing that I want to remark is that what I like of this model is the in the mechanism for symmetry breaking. We have at least 3 fields and mechanisms involved, like the usual dynamical symmetry breaking for the chiral symmetry given by the non-Bourgeois Lasignol term, the curvature of space-time that tries to restore that symmetry, and the coupling with electromagnetic fields that also compete. So it can actually also use to generate phase transitions in the early universe. Okay, so the summary. So I show a way to introduce matter fields in a gauge connection. I show how to implement it in 3 dimensions. We saw how, by breaking of the Weyl invariance, it's possible to introduce a mass gap between bosons and fermions. And we found some classical solutions. In particular, we found an interesting possibility, which is a way to embed the rotating black holes in 3 dimensions in a flat Lorentz geometry. And in 4 dimensions, we realized the model with a McDowell-Mansouri type of action, and we found these mechanisms for dynamical symmetry breaking that offer a possibility to avoid problems of fine-tuning. That's all. Thank you very much.
About your mechanism of symmetry breaking.
Mm-hmm.
something that is done by hand, or you think it's some dynamical here?
So at this level, it's a semi-classical computation. So you first give the background, and then you see how the dynamical symmetry breaking goes. So I don't know if anybody knows how to fully make computations with everything, with anything non-fixed. But at least as first or zero order, you could say it's a valid approximation.
Don't put any restrictions on it. Just take the super connection, take with all the mass reaction.
Yeah, that.
Take some background.
So
count degrees of freedom that are present.
Yeah,
do you think it's degree of freedom?
I don't think so. I don't think so because of the gamma traceless part of this composite is identically null. Otherwise, I would be very worried. But yeah, but it would be nice to also consider the system with the gravitino. So the two fields there. Yeah. But that's a different history.
Can you add conformal transformations to the connection? Take 4 dimensions SO2.4.
Yeah, I don't know. I would say that naively. I would say that in principle you can, but you will have to also check this consistency condition. So yeah, if you can, then you will end up with a I don't know. Maybe the answer is more obvious, but
If it's broken, you can still could generate scalar fields like a dilator or something.
An extra. You mean a Higgs field?
Well, Higgs fields, I was thinking more very like a scaling virus is broken, the Gaussian thought of as an example.
I think that in principle you can try to use this formulation to write some sort of n=4 super young mills with matter, with a non-fixed background. But I don't know if it's going to work. But in principle, yeah, you could write down F dual F with more for the conformal for PSU whatever, and then just do it. I don't know if it's going to